All right. Section 9.3 is what we call geometric sequences. Very similar. You'll see a lot of similarity. You'll see a lot of similarities today, or in 9.3 as there are to 9.2. Just a little bit of difference in how we write the explicit and recursive formulas. So let's get through this. What is a geometric sequence and how can I write formulas for one? So our warm-up is to find the pattern of each sequence. From 56 to 14 to 3.5 to 0.85, that's pretty clearly not going to be subtraction because this has to be minus 42, and then this is definitely not minus 42. So it's not an arithmetic sequence. Even if I try to do like second differences, these numbers are falling too quickly to be like to have a pattern with adding. So I'm actually going to try division. So what do I have to divide 56 by to get to 14? And one way to do that is actually in the calculator. I'm going to take, instead of guessing here, I'm going to take the second number, which is 14, and divide by the previous number, which is 56. So that tells me to get from 56 to 14, I would need to multiply times 0.25. And that's all fine and dandy, but this has to be a consistent pattern. So if I try that again to get from 14 to 3.5, I'm going to check to see, can I do 14 times 0.25? And that gives me 3.5. And just for good measure, if I multiply 3.5 by 0.25, I get that 0.875, which shows up here in our sequence. So multiplying by 0.25 is the pattern that we come across for that one. Okay, here from 102 to 99, I see that the numbers are falling, but they're falling gradually, so hopefully subtraction will do the trick. 102 to 99 is minus 3, this is minus 3, and that's minus 3. So there's our pattern, real simple. And then from 3 to 4 to 6 to 9 to 13, I can tell that this isn't going to be multiplication because from 3 to get to 4 is not the same as how I get from 4 to 6. So what I'm going to do here is check to see if adding works. So I add 1, add 2. Obviously, this isn't arithmetic, but I see real quick that this does have a pattern, and that is that if I go from 1 to 2, that's adding 1, and that's adding 1, and that's adding 1. And that is actually a different type of sequence that you did see a little bit of in 9.1, but something that we're not going to focus on today. So yesterday in 9.2, it was all about these sequences. This is what we call arithmetic. And today is all about actually the first sequence, which we call geometric. And that's because the pattern is multiplication, or sometimes you can think of it as division, but we're going to focus on multiplying. Okay, so we've actually kind of already done the definition. A geometric sequence has a common ratio between terms. So yesterday it was a common, or in 9.2 it was a common difference. So 9.2 is a common difference, meaning you're adding or subtracting the same amount every time. Today in 9.3 it is all about a common ratio. And we are going to stick strictly to multiplication, okay? So in order to find it, this is the same one from the warm-up, but if you wanted to find the common ratio or to find the pattern, you would take, let's say, the second term, such as 14, and divide by the previous term, which is 56, and we saw that we got 0.25. I could do that if I take the third term, which is 3.5, and divide by the previous term, which is 14. Sure enough, if I plug that into the calculator, I will also get 0.25. So what's important here is that you could also say 56 divided by 4 is 14. So you could make the argument that this pattern here from 56 to 14 is dividing by 4, but we are going to talk strictly in terms of multiplication when we talk about geometric sequences. So here the common ratio is 0.5, or sorry, the ratio is 0.25. Okay, and that's going to be a pretty important thing as we get along. So just take a look at a couple sequences quick. Are they geometric and are they not? So again, to do this real quick, you might be able to tell right away, right? For something like this, it might be an easier time. How do I get from 2 to 4 to 8 to 16? What's the pattern? Well, here I'm timesing by 2, timesing by 2, timesing by 2. Okay. So here I know that the first term is 2, and that common ratio that we have also happens to be 2. For the second sequence, from 1 to 5, that'd be, if we're talking just geometric, that'd be timesing by 5. But from 5 to 9 is definitely not times by 5. So this thing is not geometric. But it's pretty clear that this one I can just add 4, add 4, add 4. So this one would fall under the arithmetic category. And this last one's kind of fun. If I have 2 to the 3rd, 2 to the 6th, 2 to the 9th, and 2 to the 12th, you can see that the powers are going up by 3 every time, which might make you think it's arithmetic. But if we think about, I'm going to take the second term and divide by the previous term. Well, when I'm dividing things that have exponents, I can subtract those powers. So 6 minus 3 is 3, so that's 2 to the 3rd. If I take 2 to the 9th and divide by the number before, which is 2 to the 6th, again, 9 minus 6 is 3, so this is 2 to the 3rd. Okay. Finally, if I took 2 to the 12th power, which is a big number, I think it's 4,000 something, and divide by 2 to the 9th, this as well as 2 to the 3rd. So this would be geometric. This is indeed geometric. The first term is 2 to the 3rd, and that's actually also the common ratio as well. Now, I know the two examples that are on here, the first term and the common ratio matched up. Right here it was 2 and 2. Here it was 2 to the 3rd and 2 to the 3rd. That will not be the case very often. It just happens to be that way here. So the next thing we have to do with these geometric sequences is to write the formulas for them. So if you think about, let's just use, I'm going to use you just pick a random sequence. Let's start at 2 and let's have the pattern be multiplying by 3. So 2 becomes 6, becomes 18, becomes 54, and so on. Okay. The recursive sequence tells me, well, tell me the first term. Well, that's 2. And then we saw yesterday, every recursive sequence starts the same way. But then here, to get from the previous term to the next term, I'm going to multiply by 3. Okay. So that's this specific example, and then we'll put the general example next. So the next thing is, we got the recursive sequence done, but how do I write the explicit version of this? So we know the first term is 2. The second term, which is 6, we got by doing 2 times 3. The third term, which is 18, we did 2 and then we multiplied by 3 twice. You might see where this is going. To get the fourth term, which is 54, we took 2 and we multiplied by 3 times. If we wanted to keep going with this, which obviously we don't, I want to write this shorthand. The next thing is to get the fifth term, I would multiply by 3 4 times. But to show that you're multiplying by the same thing over and over, that's why we use exponents, or that's where exponents come from. So I would say this is 2 times 3 to the 4th power. To get the 10th term, that is 2 times 3 to the 9th power. So for this particular sequence, the nth term is equal to 2 times 3 to the power of n minus 1. So whatever term you're looking for, you're going to take 2 and then you're going to multiply by 3, 1 fewer than the term number of times. Okay, so I'm going to take all this and kind of make this real tiny just for reference up here. But this is the explicit formula for this particular sequence. So we've got recursive over here, which is, again, always 2 parts, and then we have the explicit over here. Okay, so that's for this specific sequence of 2, 6, 18, and 54. But if you remember here, we have A1 was equal to 2, and the common ratio between terms was equal to 3. So all we're going to do is replace the 2 and the 3 with the variables that we have here. So in general, the general form of this is A1 is equal to, and then you fill in the blank. So first term. And then A sub n is equal to A sub n minus 1 times that common ratio. Right? If you know the pattern is multiplying, just take the previous term and multiply to get the next term. So this is the general form of a recursive formula for a geometric sequence. And then here again, all we're going to do is simply swap out to find any term in a geometric sequence. You're going to take the first term and you're going to multiply by that common ratio n minus 1 times. So we have an exponent of n minus 1. And again, the explicit formula is the one that we're going to use a lot more often. So this one on the right-hand side is going to be quite a bit more useful to us as we go along. So there's the formulas for geometric sequences. Let's see how it works. Very similar to 9-2. What is the 10th term of the sequence that starts 4, 12, 36, and so on? You may be able to see very quickly that that's multiplying by 3, but just in case you don't, to find the common ratio, we're going to take the second term and divide by the first term. Sure enough, 12 divided by 4 is 3, and our first term is 4. So we're going to use that to write the formula for it, which is A sub n equals the first term times the common ratio, n minus 1 times. Okay. So now if I want to find the 10th term, I'm going to take 4 times the, now I messed this up. I shouldn't have put r. I should have put what the actual common ratio is, which is 3. So I'm going to do 4 times 3 to the 9th power because I'm finding the 10th term. Again, you're going to resort to the calculator. Geometric sequences are going to grow pretty quickly, so you're going to have large numbers very fast. So the 10th term of this is 78732. I'm going to go back here. 78,732. Okay. So there's that. And then for this next part, what is the 10th term of the sequence where A sub 1 is 2 and A sub 4 is negative 54? So this is where things get a little bit more interesting. Yesterday, or in 9.2, when we did a problem like this, we knew it was arithmetic, so we were able to just do like a slope formula. That's not the case if we have geometric, if we know that the pattern is geometric. So here's what we're going to do. We know that the first term is 2, right? That's established. That's already there. I shouldn't even write it. We know that the fourth term, in general, like if you think about it, in order to get the fourth term, you would start at the first term, which is 2, and you would multiply by the common ratio 3 times, right? To get from 1 to 4, it's 2, then second term I don't know, third term I don't know, then it's negative 54. So here I'm timesing by r, and I have to times by r 3 times to get to negative 54. Okay, so I'm going to, whoa, sorry about that. Take this, throw that up here. Okay. So now what I'm going to do is I'm going to take and figure out, to get the fourth term, I need to do times the common ratio 3 times. Well, I know the fourth term is negative 54. So now I can actually just solve for the common ratio by first dividing by 2. So there's a little bit of algebra here. We get negative 27 equals what number raised to the third power? Okay. And anytime you're trying to solve for r like this, I'm actually going to take the third root of both sides. I'm going to take the third root of r to the third and the third root of negative 27. If you recall, to do the third root, which was back in chapter 6, we do 3 math 5. That gives us the third root of negative 27, and that is negative 3. So I come back here. That means negative 3 is equal to r. So now I have enough information to find the 10th term. Okay. So to find the 10th term, I'm going to take the first term, which was 2, and times by -3 9 times. So I'm going to raise that to the 9th power. Again, just going to rely on the calculator for these things. So 2 times negative. Now, I almost made a big mistake here. You need to put that common ratio. If it's negative, you need to put it in parentheses. So 2 times -3 raised to the 9th power is negative 39,366. Where are we at? Right there. So A sub 10, or the 10th term, would be negative 39,366. 39366. Yep. Okay. So if you're missing terms, you will always set up something that contains an exponent like we did here. Okay. Applies to the real world. So the heights of consecutive bounces of a ball. So if you were to drop a ball from a certain height, it bounces back to a common ratio or a common fraction of its original height every single time. So if I would drop a ball, the first bounce comes up to 100. So the first bounce is at 100, and the third bounce is at 49. The question is, what is the height of the second bounce? Okay. And again, the way I'm going to set this up is I'm going to say, well, the third term must be equal to the first term times that common ratio squared. Because to get from 100, then a blank, then 49, I must have times by r twice. Now, I know that the number's getting smaller, so you might think I'm dividing. But again, when we're talking geometric sequences, we want to always talk with multiplication. So I'm going to do a sub 3 equals a sub 1 times r squared. Now I'm just going to fill in the numbers that we know. We know the third term. We know that's 49. Okay, so 49 is equal to 100 times r squared. Okay, so I'm going to divide both sides by 100, divide by 100. Okay, and then 49 divided by 100 is 0.49. So 0.49 is equal to r squared. Then I square root both sides, square root, and r is equal to 0.7. So that gives me the common ratio, but that doesn't give me the missing value. So to find the missing value, I'm going to go ahead and take 100 and multiply by 0.7 to get 70 is what you'll get if you plug that in. So that means that second bounce was at a height of 70 centimeters. And if we check just to be sure, that should mean if we take the second bounce and times by 0.7, I get the height of the third bounce, which was 49. Okay. So here we have our middle bounce. This right here was 49 centimeters. Okay. Now, that is helpful, but that's kind of a lot of work to get one missing number. Okay. A shortcut that we can use for this is to find what is called the geometric mean. And the geometric mean allows you to find the middle number directly, just doing one calculation. So what it doesn't tell you is it won't give you the common ratio, but it will tell you like what is the missing number right away. It's also another way, like, mean, median, and mode, or we've heard of those words before maybe. The geometric mean is just another way to measure like what's the center of two numbers. And to do that, the geometric mean is equal to the square root of the two numbers multiplied together. Okay, so all I'm going to do is multiply the two terms together and then square root that result. So let's see how this works real quick. If you know 900 blank 4, and you know it's geometric, it's been established that this is a geometric sequence, then I'm going to go to find that missing number. I'm going to go ahead and take 900 and multiply by 4, which is 3,600. and then I'm going to square root that value. Okay, and if I square root 3,600 in the calculator, I will get 60. Now here's the kicker. Calculator tells me 60, that's great. The missing number is 60. But technically, you could also live in a scenario where this thing goes from 900 to negative 60 and then to positive 4, because you can alternate between negatives and positives when you're talking about a geometric sequence. So technically there are two answers here, and either one of these would be correct. If you only give me positive 60 and you don't say like, oh, it could also be negative 60, that's fine. But understand that a lot of times with the geometric mean, there are technically two possibilities. And then for this last one, 360 to blank to 90. So if I were to take them, 360 multiplied by 90, and then I'm going to square root that result. So I'm going to do the square root of, I can just type this in right as 360 times 90. I get 180, so that's going to be the missing number there. Again, it could also be positive 180, so I'm just going to put plus or minus 180 as that missing term. Again, that doesn't tell me the common ratio. So if I wanted to write a formula for this, I would need to find the common ratio and take the second term, whether it's positive or negative 180, divide by 360, and that would give me a common ratio of 0.5. Now, of course, how that would change if you were to use the negative version of 180, then the common ratio would swap to negative 0.5, which is not a huge deal, but just be aware that it technically, depending upon whether you choose to use the positive or negative, it could be either way. So that's kind of the end of 9.3 and what we cover in Chapter 9. Here's sort of the graphic organizer for like, what if it's arithmetic? What if it's geometric? A couple things I'm going to point out here real quick, and then we'll wrap this up. That the recursive formulas are almost identical. So they both start the same. They both require you to list out what is the first term. The only difference here, and of course, if it's arithmetic, we know the pattern is adding, and if it's geometric, we know that pattern is multiplying. Okay. The more interesting thing is with explicit formulas. So I'm going to go here. With an explicit formula, they both start the same way. They both start a sub n equals a sub 1. So, give me the first term and then let's do something with it. The difference here being that with the arithmetic sequences, you are adding a common difference. And to show you're adding over and over again, we use multiplication. Okay. So here we multiply by n minus 1, multiply by n minus 1. Whereas in the explicit formula for the geometric, the pattern is multiplying, which is great. We have times r. But to show that you are multiplying by the same thing over and over, we have to use an exponent. And that's what can throw students off is that in arithmetic, it is adding, but you have to use multiplying when it comes to the explicit formula. So I'll leave this on here. This is kind of a good overall, overall information, kind of an overview of 9.1 and 9.2, 9.2 and 9.3. So we kind of get an idea of what all that stuff is. The homework for 9.3 is, again, very similar to 9.2. So give that a shot and come back with questions you have.